Our ancestors ate each other. Scientists have found evidence that close evolutionary relatives of humans killed and possibly ate each other. Clues to this conclusion come from a 1.4 million-year-old fossilized shin bone belonging to a mysterious human relative, which bears traces of stone tools, believed to have been used for cutting flesh. Based on the marks preserved on the ancient bone, it appears someone was hungry enough to eat the leg of our distant relative living in what is now Kenya, some 1.45 million years ago. A team led by Brianna Pobiner of the Smithsonian Institution's National Museum of Natural History conducted a detailed three-dimensional analysis of the cut marks discovered on the ancient shin bone. The researchers also conducted experiments on the bones to determine what might have produced them. They believe the fossilized bone represents the oldest example of hominin-on-hominin butchery, and the marks on it were most certainly made by stone tools, resembling flaying meat in preparation for a meal. The description and results of research on the ancient shin bone were published in the journal Scientific Reports. A 1.45 million-year-old shin bone was discovered in northern Kenya in the early 1970s. It belonged to a relative of Homo sapiens. Initially thought to belong to Australopithecus boisei, then to Homo erectus, and now scientists say they don't have enough data to assign it to a specific species. But it certainly belonged to our ancient relative. Several intriguing cuts were found on the bone. Analysis of these cuts revealed that they were made with stone tools. This, in turn, suggests that the leg's owner was a victim of cannibalism. The information we have tells us that hominins likely ate other hominins at least 1.45 million years ago, Pobiner said. There are many other examples of species in the human evolutionary tree eating each other, she added. Pobiner first stumbled upon the fossilized shin bone in the collections of the National Museum in Nairobi, Kenya, while searching for clues about which prehistoric predators might have hunted and eaten ancient human relatives. Although humans, our relatives and ancestors, held a top position in the food chain for the past few million years, they sometimes ended up as meals for these ancient beasts. She examined the shin bone for tooth marks, but instead noticed what immediately looked like an example of cannibalism. Pobiner used a material dentists used to create tooth impressions to create a model of the bone. She sent it to Michael Panty of Colorado State University for analysis. She didn't provide any details about the submitted material, simply asking him to analyze the cut marks. Panty created 3D scans of the molds and compared the shape of the marks on the tibia with a database of 898 tooth marks, cut marks, and other bone damage made in various controlled experiments. Analysis clearly matched 9 of the 11 cut marks to the type of damage inflicted by stone tools. The remaining 2 marks were bite marks from a large cat, most likely a lion. According to Pobiner, the bite marks could have come from one of 3 different types of saber-toothed cats that roamed the area at the time the tibia's owner was alive. The cut marks alone don't prove the leg's owner was eaten, but Pobiner pointed out that this seems the most likely scenario. She explained that the cut marks are located where the calf muscle attaches to the bone, a good place to cut if the goal is to remove a piece of flesh. All the cut marks are also oriented in the same way, so that the hand wielding the stone tool could have made them all in sequence without changing its grip or adjusting the cutting angle. The cuts look very similar to those I've seen on fossils of animals that were processed for consumption. It seems most likely that the meat from this leg was eaten, and that it was eaten for nutritional purposes, not ritual purposes, Pobiner said. It was also considered that the incisions could have been made for reasons other than cannibalism, although cannibalism was more common in our history than one might think. They could have been ritualistic, part of the burial process. Carving the bones of others, or making decorative objects from bone, such as combs, pendants, and other jewelry, was common. However, in this case, the analysis pointed to cannibalism, although the term actually refers to the practice of eating members of one's own species, and in this case, we are not necessarily dealing with the same species, as it's possible that this was a feast of one species eating its evolutionary cousin, which would mean that it wasn't, strictly speaking, cannibalism. It's unclear which marks on the bone appeared first. Perhaps our relatives ate the flesh of an ancient lion's prey, or perhaps the lion benefited from the bones left by the perpetrators of the murder. This is impossible to determine. We don't know which species ate, or even who was eaten. The use of stone tools also doesn't determine which species might have been involved. Every city has its own microbiological fingerprint. Each city is inhabited by a unique set of microbes. Scientists say this is a distinctive microbial fingerprint. It's so unique that the owner's hometown can be identified based on the material on the sole of a shoe. The researchers reached these conclusions after analyzing thousands of samples taken from places most frequently visited by people. Swabs were collected, among other places, from handrails in subway stations and bus interchanges in 60 cities around the world. In total, over 4,700 samples were analyzed. Using DNA sequencing, the scientists were able to create a global atlas of the urban microbial ecosystem. This is the first catalogue of its kind in history. The research results are presented in the journal Cell. The research results indicate that, microbiologically speaking, no two places in the world are identical. Each of the analyzed metropolises has a unique set of microbial species that distinguish it from other places. The 3-year study also revealed thousands of previously unknown microorganisms, including nearly 11,000 viruses, and over 1,300 types of bacteria. None of them matched any previously known species. Every time you take the subway, you can encounter a completely new species of microorganism, says biologist Christopher Mason from Cornell University. The research team consisted of dozens of scientists from over 60 institutions. The scientists collected samples from 32 countries on 6 continents. Initially, their goals were less ambitious, but the results surprised everyone. The scientists' work generated enormous interest, leading Mason to found MetaSUB, an international organization dedicated to documenting the urban biome that millions of people encounter every day. According to the researchers, it's clear that cities have a profound impact on human health, although the mechanisms behind this impact are diverse and often poorly understood. Our understanding of microbes in urban environments is only just beginning, the researchers write in their paper. The research findings support this claim. Among the 4,728 samples analyzed, all of which were collected before the COVID-19 pandemic, a significantly greater number of completely unknown microbes were discovered than known ones. A total of 10,928 viruses, 1,302 bacteria, and 838,532 viral DNA fragments were identified that had no counterparts in reference databases. Only 4,246 species of urban microorganisms had been previously identified. Scientists identified a set of 31 microbial species that was common to 97% of the samples. This core urban microbiome appears to be present virtually everywhere around the world. Beyond this core, there are distinct differences in microbial populations within each city. These differences are so significant that analyzing a residence would allow one to determine with 90% accuracy where a person hails from, Mason says. The microbiome contains molecular echoes of the place where it was collected, explains study co-author David Danko, Director of Bioinformatics at MetaSUB. A sample from the coast might contain salt-loving microbes, while a sample from a densely populated city might show striking biodiversity, he says. In addition to distinguishing the distinct signatures of each urban microbiome, researchers hope to uncover potential threats to human health. The research may lead to new ways of identifying antibiotic-resistant strains of bacteria. Scientists still don't know whether the microbiological uniqueness of each city is a matter of chance, or whether other factors, such as geographic differences, are at play. Research aims not only to discover pathogens that pose a health risk. The world of invisible microbes in cities may also hold promising medical possibilities. Thanks to it, scientists can discover new compounds that will help develop more effective drugs and antibiotics in the future. Synthesizing similar compounds is the next step in research, Mason argues. People often think of the rainforest as a wealth of biodiversity and new molecules that can be used for therapy. It turns out the same is true for subway railings or benches, he adds.